we've defined reductions. The next bit is to define hard problems or complete problems for a certain class. That's how we went from polynomial time reductions to the notion of NP hardness and NP completeness, which gave you this strong statement, right? The one for all for one. Either this single problem has a polynomial time algorithm, or all of NP doesn't have. So we'll try to do the same thing for these parameterized reductions. So we need an analog of NP. We know, or intuitively, FPT is playing the role of P, the efficiently solvable algorithms in a parameterized sense. But we need the kind of superset of things that we cannot really solve efficiently, but we have to somehow have a universe of problems to talk about. And that's not as obvious what to pick here, but one choice could be this class that's been called para-NP, so parameterized NP. I think it's a natural definition. You say we still allow FPT algorithms. And remember when we went from P to NP, we said instead of polynomial time, we now allow non-deterministic polynomial time, where we allowed the machine this magic guessing operation, where it could essentially, with divine insight, take the right of two paths without knowing which one it is. Formally defined in Turing machines as there's many possible computations, and if any one of them leads to an accepting configuration, the overall input is accepted, even if there's one out of exponentially many. So the same we can do here. We allow a non-deterministic machine, a non-deterministic Turing machine, but we allow it an FPT number of steps. Right, so same as before. That's some function of the parameter that's arbitrary, and then a polynomial in the input size. Same notion as before. Indeed, this class has a few promising properties. I'm not going to prove those. You'll see soon why. First of all, it's closed under FPT reductions. What's that supposed to mean? Well, if I have a problem and I can reduce the problem, so say some problem A is in para-NP, and I can reduce some other problem to this problem A, then I know B is also in para-NP. Another nice consequence is FPT is equal to para-NP, which again, we shouldn't think is a likely thing. Right? This means I can use the full power of non-determinism in an FPT algorithm, and that doesn't allow me to do more than doing it deterministically without any guessing. But the two are the same if and only if P and NP are the same. So it's kind of a strong way of saying if I have problems in there, unless P is equal to NP, I won't have an FPT algorithm. And you can also prove something similar to a kernelization for this class. So you can, again, transform this general FPT time into a pre-processing step, and then something that's just bounded in terms of the parameter. And because the class is so analogous to NP, we can also define hardness in the same way. We can say a parameterized problem is para-NP hard if every other problem in para-NP can be FPT reduced to it. Exactly the same as we defined NP hard. Every problem in NP can be polynomial time reduced to that problem, then that problem is NP hard. So same thing here, except that we have to carry through the parameterizations and use FPT reductions. So we should be happy because that sounds like a nice theory. It has all the good properties we would want of a complexity class. And it seems to nicely play with P and NP. Now, the problem is that it actually plays too nicely with P and NP. And let's prove this theorem, and then I'll give you the interpretation afterwards, because the proof nicely shows the absurdity of para-NP completeness. So formally, the statement is as follows. We have some non-trivial parameterized problem. Non-trivial just means it's not everything a yes or everything a no instance. That's all that means. So some parameterized problem that is para-NP complete. Then indeed, the restriction of that problem to bounding the parameter by some constant is NP hard already. I guess this is a bit sloppy. There exists a constant d so that the restriction is already NP hard. Let's see why that might be the case. So we got to work with what we have, right? So let this L and kappa be para NP hard or para NP complete. We need it to be, well, it is para NP complete, so let's not worry about it. And let further some other language let L prime be NP complete. So we have to somehow connect these two. So we'll define a boring parameterization, kappa 1, that just outputs 1 for every input. It's the constant parameter. Well, if L prime is NP complete, that means L prime and kappa 1 is in para NP. Why? Well, we have to show that there's a non-deterministic FPT algorithm for this parameterized problem. I should say non-deterministic. Because the problem is in NP, there is a non-deterministic algorithm to decide it in polynomial time. And that same algorithm is also FPT time, because FPT includes polynomial time. And we actually don't need the parameter to be anything. It can be 1. That's what it says here, to use kappa 1. So the same algorithm is also a non-deterministic FPT algorithm for this parameterized problem L prime and kappa 1. Right. Now we use that we have a para-NP complete problem. So there has to be a reduction from this problem to L kappa. No. Which means there's some algorithm, I haven't used a name for this, so there exists an algorithm A. Just going from the definition of FPT reduction. So x is in L prime if and only if A of x is in L. That's the equivalence. And the running time of A has to be FPT in the input. So it's f of kappa 1 of x for some function x and n to the c or say size of x to the c for some constant c. But really this means just a constant factor because kappa 1 is always 1, right? So whatever f does, it can only be some number. Yeah, I was a bit ambitious with the space here, I think. So this is actually it's polynomial in the size of the length of x. Well, that's essentially it, right? So okay, this internal here is 1. That means f of 1 is some constant. Let me use my my new page now that I made it anyways. So the running time of A is actually polynomial in X. And that also means we also have an algorithm B for our parameterized problem here. Let's put that here. So because L kappa is in para NP, there's an algorithm B deciding L in FPT time, some function f prime of k times n to the c, n to the d, whatever. Let's say c prime. Now we're just chaining these two things together. Okay, we can take an input for L prime, we map it via A to the problem L, and then we take this FPT algorithm B to solve it. So if I take B and apply it to the output for A, this decides L, L prime. Sorry, that part is useless because that's a non-deterministic algorithm. Forget about it. I don't think we need that. The thing is that we reduce this NP-hard problem to a slice of L where the parameter is bounded by a constant. And so A itself it maps this NP-hard language L prime to a language L lesser equal D, where D is just f of 1. That's exactly our unknown constant, but it's given by f of 1, some constant. That's the set of all inputs in L where the parameter is bounded by this constant. So L transforms this NP-hard language to this language, and it's a polynomial time reduction because its running time is polynomial in the input size, right? So what we've actually shown is that L prime polynomial time reduces to L less or equal D. And that was an NP-hard language. So also this one is it's NP-hard. Okay, I'm gonna try to write it a bit clearer. And that's all we wanted to show. And this part is correct, but useless. Sorry for the confusion. All right, so we've shown whenever a problem is para-NP complete, already the restriction of the problem where the parameter is constant has to be NP hard. So what this means is that really almost no interesting problems are para-NP complete. They cannot be. In particular, all of these cannot be para-NP complete because if you bound the parameter by a constant, the resulting running time is polynomial. Remember, for each of these problems, a trivial solution is to go through all subsets of size k. That's an n to the k algorithm. It's not polynomial, it's not FPT, but if k is a constant, then it's polynomial. That's the important distinction between FPT and what's also sometimes called XP. So the problems where if you bound the parameter by a constant, then the resulting running time is polynomial. These are much weaker guarantees than FPT. Okay. I'm not officially introducing XP, but that's these problems. So you could say it's n to the order k, or even worse, I guess. But that's what the running time for these is. So this notion is much too strict, and it won't help us for the interesting questions here. So problems where there's some hope to get a good algorithm, but it doesn't seem to work with an FPT time. It doesn't help us tell why that is the case, why these problems don't really seem to allow an FPT algorithm. So we'll have to brush up the theory a bit to make that distinction. There are problems that are para-NP complete, for example, graph coloring, where the parameterized P graph coloring is para-NP complete, but that's virtually just the case because also 3 coloring, where the parameter is 3, is already NP hard. Okay.